Hello everyone. So in the last video, we solved logic gates using the gate level modeling. So in that video, I did one mistake. In this NOT gate, I wrote two inputs, but we know in the NOT gate we have only one inputs. Okay, so that's why in the simulation we got some unknown values, right? So just rewrite and just simulate. You will get exact result. Okay. So today we will solve logic gates using the data flow modeling. Okay, so first understand what is the data flow modeling. And in the data flow modeling, we can directly write the expression for our output. So based on that expression, that output will come. Okay, so that is the data flow modeling. So in this question, this code is same as the our gate level modeling based question which we solved in the last video. So here same, two inputs A, B and output. What are the outputs? AND, OR, NAND, NOR, NOT, XOR, XNOR. These are the outputs. Okay. So for this data flow modeling, we need to write assign and output. This is our output for AND gate implementation, right? So AND equal to A and B. For NAND gate is the negation of AND, right? So that's why negation A and B. For NOR, negation A or B, and for NOT, negation of B. So we have two inputs, right? So but I choose only B input, so negation of B. Next for XOR, this is the expression A XOR B. For XNOR, negation of A XOR B, right? So this is the Verilog code for logic gates using this data flow modeling. Okay, similarly I wrote test bench. Okay, so this is the test bench, and this test bench is same as what we wrote in the last video in that gate level modeling. Okay, same. For input we wrote array AB, for output wire, and then module instantiation. Then in this initial block we wrote conditions for inputs. When equal to 0, b equal to 0, then after 10 seconds 0 1, then after 10 seconds 1 0, then 1 1, then after 10 seconds finish. So this is the test bench for this module. Okay, now let's simulate and see output. Okay, so this is the simulated result. Okay, so for initially 0 0, then 0 1, then 1 0, then 1 1. Okay, for AND gate, when both inputs are 0, then output is 0. For 0 1 0, 1 0 0, and for 1 1, when both inputs are high, then output is high. Okay, now let's check it for OR gate. For 0 0 case 0, for 0 1 case 1, for 1 0 case 1, and for 1 1 case 1. It means for any one input is high, then output is high. Okay. For NOT gate, in this NOT gate we choose negation of B, right? We have two inputs, but we choose only one input, that is B. So negation of B means when B equal to 0, then this one is 1. For when B equal to 1, then this not output is 0. For B equal to 0, then again 1. For B equal to 1, then again 0. Okay. Then next NAND gate. NAND gate is the negation of AND gate, right? So for 0 it's 1. When AND is 0, NAND is 1. Here also AND is 0, so NAND is 1. And when AND is 1, then NAND is 0. Similarly, NOR gate is negation of OR gate. Okay. Then XOR gate. XOR gate when both input 0, then XOR is 0. When 0 1 case 1, 1 2 case 1, and when both input are high, then also our XOR is low. Okay, and XNOR is a negation of XOR. So you can see here it's the opposite of this XOR result waveform. Okay, this is the simulated result for this logic gate using the data flow modeling. So in this way we wrote this code in data flow modeling, and we wrote this test bench, and we simulated and we observe our output. So we will solve few more questions in the upcoming videos. Till that, thank you.